start a second lecture of supersymmetric field theory by Schlomo Razamat. Yes, please.
Thank you very much. So let me start the second lecture. So I remind you that our goal in these lectures is to understand in a certain geometric way strong coupling dynamics of quantum field theories in 4 dimensions. And in last lecture, we started developing a toolkit to do that. Okay, so I will remind you briefly the tools that we have discussed, and we will continue today discussing the tools and start discussing some interesting dynamics. Okay, so let me start with a very brief summary of what we did last time. So we discussed various tools which will help us understand RG flows, knowing something about the UV fixed point, deduce something about the infrared fixed point. So we discussed the anomaly polynomials in 4 dimensions being invariant under these flows. And these statements about anomaly polynomials don't rely on supersymmetry. And then we have discussed various supersymmetric quantities or properties that will help us to deduce physics. So using supersymmetry, we discussed that there is this very important symmetry that we can use to do very interesting stuff, which is called the R symmetry. In particular, we have related or mentioned that it is possible to relate the A and C conformal anomalies to 't Hooft anomalies of R symmetries. So the A anomaly is 9/32 trace R cubed minus 3/32 trace R, and C equals 9/32 trace R cubed minus 5/32 trace R. And here I remind you that the R symmetry that we use has to be the superconformal one. Okay, so there is a caveat in this relation. There is a special R symmetry, which is part of the superconformal group, and this relation holds only if we use that R symmetry. And we also discussed how to determine the superconformal R symmetry if we have a flow from a UV theory to an IR theory, and that procedure is called A maximization. Okay, and it involves a certain assumption that we have identified all the abelian symmetries in the infrared. Some of the symmetries might emerge. So if there are emergent symmetries in the infrared, for this procedure to be correct, it is important that they will not mix with the R symmetry in the infrared. So in general, the R symmetry in the infrared is some combination of the R symmetry in the UV and abelian symmetries that we can have. And the statement is that we define this trial A anomaly as a function of this parameters alpha, and we maximize. Okay, and then the superconformal R symmetry is the one which we obtain by performing this procedure, and it is given by this combination. And from this combination, we then, for example, can deduce the conformal anomalies of the theory in the infrared. Next, what we discussed is deformations. Okay. And the deformations that we discussed are supersymmetric and preserve our symmetry. Okay. These will be the only deformations that we will discuss, as this will give us the tools to deduce something about the IR dynamics. So there were 2 types of deformations we discussed. One was the superpotential deformation, when we add to an action certain integral over the space and half of the superspace of lambda times O, where O is some chiral operator. And the properties of this deformation depend on the R charge of this chiral operator. So if this R charge is smaller than 2, then the deformation is relevant. If the R charge is equal to 2, it is marginal. Okay, and if R charge is bigger than 2, it is irrelevant. Another deformation we considered was gauging certain subgroup G of the global symmetry group of the UV CFT. And here we said that if we compute the 't Hooft anomaly of trace R with G squared, and this anomaly turns out to be positive, then the gauging is relevant, okay, or asymptotically free. And if trace R G squared is 0, the gauging is marginal. Okay, and also we have mentioned that this division of deformations into relevant, marginal, and irrelevant is a little bit tricky one if we can turn on several deformations, and there is something called dangerously irrelevant deformations, and we need to be aware of them. And if you want to analyze, flow starting from certain CFT, a way to do it in a consistent way is to turn on each time a single deformation. To turn on a deformation, flow into to infrared, analyze the spectrum of relevant, marginal, and irrelevant operators again, and then turn on another relevant deformation or exactly marginal deformation, and so on. And the final thing that we have discussed, and we will continue discussing today, is when marginal operators are exactly marginal or marginally irrelevant. Okay, we have discussed that in supersymmetric theories. These are the only two options. There are no marginally relevant operators. Operators can be either marginally irrelevant or exactly marginal. And the way to deduce, or to find the exactly marginal operators is to compute the following quotient. So MC we have defined to be the conformal manifold, the space of exactly marginal deformations. And to compute it, we list all the couplings of marginal operators that we have in the theory, including gauge theories. If we have a gauge theory, this will be e to the 2 pi tau I, where tau is the complexified coupling of the gauge group. And then we compute the following quotient. We quotient this set of couplings by the complexified symmetry group. So this symmetry group here is the symmetry of the UV of the theory we start with, of the CFT we start with. And if we gauge a symmetry, this symmetry is the one which is commuting with the gauge symmetry, including the anomalous symmetries, as we have stressed. Okay. Any questions about this? Okay. If there are no questions, let me briefly go over the example that we started doing last time, and we did not finish it, and I will finish it now, of a detailed analysis of a conformal manifold of a theory, which will turn out to be very interesting. Okay, so the example we have started to discuss is the SUN gauge theory with 3n flavors. Okay, so as we have discussed, this means that we have 3n fundamental fields Q and 3n anti-fundamental fields Q tilde. Okay, and what we have discovered is that the gauging in this case is marginal. Okay, and for general n, by general we mean n isn't equal to 3, we found that it is actually marginally irrelevant. And the reason it is marginally irrelevant is, as if we compute this quotient, in this particular case, the only marginal coupling is the gauge coupling, okay, of the SUN gauge group. And the symmetry here involves the anomalous symmetry. So this is equal to U1 anomalous, under which the fundamentals and anti-fundamentals have the same charge, and other symmetries. Under the other symmetries, the gauge coupling is not charged, but by definition of a symmetry being anomalous, the gauge coupling shifts under this symmetry. So we have only one symmetry. We look for invariance under that symmetry when we compute these types of quotients, and we cannot build any invariant, any holomorphic invariant from this single coupling. So that means this quotient is empty, and the theory is free. So the only fixed point we have is the free theory when we set the couplings to 0, and we cannot move out of this point using exactly marginal deformations. Okay. And
excuse me, may I ask
yes,
a question? So
sure.
In the previous slide, you gave a criteria which is related to yes, you gave a criteria which tell us the deformation is relevant or marginal. Is this only true to the one loop order?
That's right.
Oh, okay.
Okay. Yes, this is important. This is only at the one loop order. This is the perturbative. This is the leading perturbative contribution. So if you want to move a little bit out of this fixed point that you started with, you want to understand where you will flow. Okay, and this is, as you remember, exactly was the caveat of these dangerously irrelevant operators. This analysis is done only in the vicinity of the fixed point, and then if you move too far, this analysis can fail. Okay, does this answer your question? Okay, so next what we do, we perform the more detailed analysis in the case of n equals to 3. And as we have discussed, in the case of n equals to 3, we have additional marginal operators, which are given by baryons and by antibaryons. So by baryons, we mean a certain gauge invariant combination of 3 Qs, which involves an epsilon symbol. And by antibaryons, it is epsilon times Q tilde Q. And the reason why these operators are marginal is that at the free point, the Qs have R charge, which is equal to 2/3. So the baryon operators have R charge, which is equal to 3 times 2/3, which is 2. And the same holds for the antibaryons. So these operators are marginal. And if you wish for other values of n, the baryons are q to the power of n. And for n, which is bigger than 3, they will have a large R charge and they will be irrelevant. And for n equal 2, these baryons, which basically are the same object as the mesons, will be relevant operators, some mass terms. So only for n equals 3, these operators are marginal. So if we have these marginal operators, we can turn on superpotential couplings of the form lambda times a b plus lambda tilde times a b tilde. Okay, these b and b tilde, there are many of them. Since we have 9 flavors for n equals 3, we have SU9 flavor symmetry group rotating the Qs and SU9 rotating the Q tildes. So we have the SU9 times SU9 symmetry and U1 baryonic symmetry and another U1 which is anomalous. And under these non-abelian symmetries, the baryons transform as 84-1 or 184, where this first factor is the representation under the first SU9 and this under the second. And we have the charges under the baryonic and the anomalous symmetry. So say the charge of the under the baryonic symmetry is plus and minus for these two guys. And under the anomalous symmetries, these guys have the same charges. And the charges we assign to the couplings are conjugate to these ones. Okay, so that the superpotential will have 0 charge if we assign charges to the couplings. I think I saw, I cannot see the questions in the chat, so it appeared for a second, it disappeared for me. So if you have a question, please just ask it. So, or Wenbin, if you can read it, it will be helpful. Okay.
Sorry?
Yes.
So what was your question?
I think there was a question in the chat, or I am mistaken.
No, no, no. I just sent out your notes yesterday. Just
Oh, you sent it again. Okay, thank you. Okay, so now the quotient that we need to compute to find the conformal manifold of this theory is just we list all these couplings, lambda, the baryonic coupling and the antibaryonic coupling, and the gauge coupling, and we need to quotient by SU9 times SU9 times U1. Sorry. Okay. Times U1 baryon and times the anomalous symmetry. All these symmetries complexified. We need to compute this quotient, find its dimension, and that will be the dimension of the conformal manifold. This is a well-defined mathematical problem, but it is very hard to perform in general. Okay. You even can, there is a way to just feed it into, say, Mathematica, to rephrase it in a way that Mathematica will compute for you, but for large groups and large representations, this will be a hard problem to perform. So the way we will analyze this quotient, and I will do it in a little bit detail as it will be important later on, is by using certain tricks. And this analysis will involve several steps. So the step number one will be to find some direction which is exactly marginal. So I will, the derivation of this direction uses techniques that I'm not reviewing in these lectures. I did add an appendix to the notes where I do it. It's not very hard, so I ask you to believe me that this direction is exactly marginal, and I will perform an important check of this statement. And then starting from this one direction, we will find other directions which are exactly marginal on this conformal manifold. So this direction on the conformal manifold was found in a seminal paper by Lee and Strassler, which was maybe the first paper which analyzed in great generality the questions of conformal manifolds. So the statement of Lee and Strassler was that the following deformation of this theory is exactly marginal. We take one coupling which we call lambda, so it's just one number. Here, this is a collection of coupling. Okay, maybe it's a bad name, let me call it alpha. There is one coupling, and we multiply it with the following operators: Q1, Q2, Q3, Q4, Q5, Q6, plus Q7, Q8, Q9, and the same for Q tildes. Okay, we split the Qs into groups of 3. Okay, Q7, Q8, and Q9. And the claim of Lee and Strassler is that this deformation with a single alpha plus gauge coupling, which is related to alpha, is an exactly marginal deformation. Okay, and let us perform an important check of this statement. So what is the symmetry that this deformation preserves? So this deformation breaks the SU9 symmetry, which rotates the 9 Qs to SU3 to the 3. So the symmetry which is preserved is SU3 to the 3. So SU9 is broken to SU3 to the 3. Both SU9s are broken to SU3 times SU3 cubed. And this is the only symmetry that we have along this direction. So remember that when we discuss the logic of this quotient, we have mentioned that the only way for a marginal operator to become marginally irrelevant is if it absorbs or eats a conserved current. Okay, this is very similar to Higgs mechanism logic. So let us analyze how the marginal operators that we have in our theory decompose under this symmetry which is preserved along this direction. So it is a simple group theory exercise. So we have 84 of SU9 and we want to decompose it under SU3 cubed symmetry. So how does 84 decompose? Well, it has 3 singlets. And then we have sum of I not equal to j, 3i times 3j bar, where I and j label the 3 different SU3 symmetries. And then we also have plus 3, 1 times 3, 2 times 3, 3, 3. Okay, so we have 3 SU3 symmetries, and 84 of this SU9 decomposes in this way. So there are 3 singlets of these SU3 symmetries. There is something which is in fundamental of all of these SU3 symmetries, and there are these bifundamental collections of operators. On the other hand, the adjoint representation, which is 80 of SU9, decomposes in the following way. So we have 2 singlets, and we have then 3 adjoints for the 3 SU3s. And then we have the same type of combination of bifundamentals. Okay. So now it is important that what the symmetry that we want to remain will be only these 3 SU3s which have these adjoints. It means that the rest of the components of these conserved currents have to be absorbed by something in the marginal operators. And you see that the decomposition into these SU3s of 80 and 84 contains the same types of structures. So we have these bifundamentals here and here. So these guys can be absorbed by these guys, okay? And if we do this computation, so we have the 84, 1 plus 80 plus 184, which are the marginal operators, lambda and lambda tilde, and we have the one operator coming from the gauge coupling. If we subtract from it the conserved currents that we have coming from the SU9 times SU9 times the 2 U1s, so we have 81 minus 180 minus 1, 1 minus 1, 1. If you do this computation, you find that the result is that we have 1 plus 3, 1 times 3, 2 times 3, 3. These are the 3 SU3s coming from one SU9. And then we have another guy like that we call it 3, 4, 3, 5, and 3, 6, which comes from the other SU9. So we have 2 SU9s. One is broken to 3 SU3s and another to 3 SU3s. And then we have the 6, the adjoints of the 6 SU3 symmetries that we have. So this is a very non-trivial consistency condition on this of this claim. So this one that we see here is the exactly marginal deformation. Then we have additional marginal operators in these representations, and these guys are the conserved currents of the remaining symmetry. So you could ask, maybe there is another way to break the symmetry and find an exactly marginal deformation. You would need to do this type of computation. You would need to show that the symmetry, that the marginal operators are such that the conserved currents which are broken can be eaten by certain marginal operators, which become marginally irrelevant. So these guys become marginally irrelevant, and these still remain marginal on this submanifold. Are there any questions about this? Okay. So what we have actually found is that there is a direction of this on this conformal manifold. Let us call it the Lee-Strassler direction, on which the symmetry is broken to SU3 to the 6. So now what we can do, we just can continue analyzing the remaining marginal deformation. So it's step 2. We look on the marginal operators that we are left with, and these are these 3, 1, 3, 2, 3, 3, plus 3, 4, 3, 5, 3, 6 that I've mentioned. So this is already an exactly marginal deformation. So if we are on this direction on the conformal manifold, this exactly marginal operator is not charged under any symmetries. It's exactly marginal, but these are marginal operators. We still need to understand whether they lead to exactly marginal operators or marginally irrelevant ones. So for example, we can take one of these guys, and if you turn on this coupling, which is in this representation, and a natural conjecture is that the group which is preserved is the diagonal combination of the 3 SU3s. Okay, so let us decompose this operator, this marginal operator, in a representation of the diagonal combination of the 3 SU3s. So what you will get is you will get that there is a singlet, there is an operator in 10-dimensional representation of this diagonal SU3, and there are two adjoints of this diagonal combination. On the other hand, if you decompose, on the other hand, you have these three SU3s, which are the adjoint or representation of these SU3s is just the adjoint representation of which one of them, and under, when you go to a diagonal combination, they become just three adjoint representations of the same group. And again, we want to have only one SU3 remaining, so two of these three SU2s need to be eaten by something, and we have exactly the same structure in these marginal operators. So what happens if we turn on this type of deformation? We can have a one exactly marginal deformation given by this one, on which the group SU3 to the cubed is broken to a diagonal SU3. So we have another exactly marginal deformation where one copy of SU3 cubed is broken to SU3, to the diagonal SU3, while the other SU3 to the cube remains. Okay? So this is another direction on the conformal manifold. Of course, you can do it for the other collection of exactly marginal operators, which are, for the marginal operators, which are in this trifundamental. And this will give you yet another direction of the conformal manifold, but now you preserve the other SU3 to the cube and break another SU3 to the cube to an SU3. And then if you turn on both of these deformations, in general, you will preserve only SU3 square deformation. So what is the dimension of this subspace? So we have the one dimension that we originally had, and then each one of these breaking gives us another marginal deformation. So in total, we have 1 plus 1 plus 1 exactly marginal operators plus 10 operators in 10-dimensional representation of two of the unbroken SU3s that we have. So we have a 3-dimensional exactly marginal manifold, submanifold, which preserves SU3 to squared symmetry. In the next lecture, we will actually have a geometric interpretation of this conformal manifold. We will see that you can think of this conformal manifold, this 3-dimensional conformal manifold, as the complex structure moduli space of a 6-punctured sphere. So this will be, I detail this example here in a bit of an annoying technical detail, because it will be important for us in this geometrical framework of thinking about things. So this is the second step. We still have marginal operators, and we can continue breaking them. So we can turn on now operators in the 10-dimensional representation. And if we turn on these operators, this will break completely the one of the two SU3 symmetries. So we'll have 1 plus 1 plus 1 that we had before. And then each one of these will give us additional 2 deformations. So we can go in first step by adding 2 of these deformations. And then, as we will see geometrically, this will correspond to a sphere with this 5-dimensional conformal manifold will correspond to a sphere with 8 punctures of certain types. Okay, let me write it quickly here. And in the last step, we can turn on also these marginal operators, the remaining ones, and we'll obtain a conformal manifold which has dimension 7, on which no symmetry is preserved. Okay, and this will correspond to a sphere with 10 punctures in what we will see later on. Okay, so even in this very, very simple example of theory, which is a conformal quantum field theory, just SU3 with 3 end flavors, there is a very interesting structure of the conformal manifold. And again, to give you something that we will derive for this theory, we will see that there is actually a geometric meaning for this conformal manifold. Okay, do you have any questions? Okay. So this analysis of conformal manifold is a very fun group theory exercise. So this is what usually happens, or often happens with supersymmetric theories, with analysis of supersymmetric theories, that eventually an analysis of complicated physics reduces to certain counting problems or to certain group theory problems. So this was a group theoretic problem. And now I will discuss the last tool we will need to analyze supersymmetric dynamics in this set of lectures, and it will be related to certain counting problems. Okay. So final tool that we will discuss.
Oh, excuse me, I think
yes.
I didn't follow your previous analysis. So
Okay.
what do you, maybe the question is that what's the meaning of these numbers? Are they the dimension of the?
These are the number of exactly marginal deformations that your theory has. Okay, so
but
you have
at the very beginning step, it seems I only have 3 parameters.
Which
that
step?
is 2 baryon, the 2 baryon operator and one gauge.
Okay, thank you for asking me. Let me clarify that. So so let me go here. So when I wrote, what are these couplings, right? These couplings, let me write these baryons explicitly. So these couplings I wrote, they couple to the baryonic operators. I was a little bit schematic. I was more detailed in the last lecture. So what are these baryons? Okay. So we have, let me write it like that. So how do we build these baryons? So we have a SU3. So we have to build an invariant, the gauge invariant. We have this epsilon symbol, and then we have this fields Q, which are in fundamental representation, Qi, Qj, Qk, sorry, Qj, Qk, but they have additional indices, this A, B, and C, right? We have 9 Qs, okay? So since we anti-symmetrize these epsilons, we need to anti-symmetrize these ABCs. So what we get is a baryon which has 3 indices, but which are anti-symmetrized. So this guy is in 84-dimensional representation of this SU9 symmetry. Okay, so we have 84 baryons. In particular, that means that we have, when we write that the coupling is lambda dot b, we have 84 different couplings that we can turn on. Each one of these couplings is marginal. Okay, the same holds for the antibaryons. So this is 84 couplings. This is 84 couplings, and there is another marginal coupling.
I see.
So there are a lot of marginal couplings, and in the end of the day, only 7 of them are exactly marginal. The rest are marginally irrelevant.
I see.
Okay, thank you for
so in the following, you just try to use the representation in your gauge in your global symmetry group to cancel the representation of
right.
This kind of things. Okay.
That's right. You know, in the end of the day, the answer turned out to be simple. So the answer, what is the dimension of the conformal manifold here? So we have these marginal operators written here, and we have a dimension of global symmetry that we have at our starting point, free starting point. And in the end of the day, the dimension of the conformal manifold is just the number of marginal couplings minus the conserved currents. This is true because we could break the symmetry, the global symmetry, on a generic point of the conformal manifold completely. Okay, so we could absorb all the conserved currents completely, and the difference was this 7. So that's what remained. But we also analyzed, you know, as submanifolds of these conformal manifolds on which you break only part of the symmetry. Okay, is this clearer?
Yes.
Okay, thank you. Any more questions?
I just want to ask, for each step you are breaking is symmetry. You get 6 puncture Riemann surface, 8 puncture, and 10 punctures at the end.
Yes.
And do you have some description of what are these field theories?
So we will discuss this in the next lecture in great detail. Oh. Here I give you just, you know, we have this quantum field theory, and we'll have a geometric construction of it, which will have a Riemann surface in it with punctures. And we will be able to think about these submanifolds of this conformal manifold in terms of these geometric constructions. Okay, so next lecture, when we will discuss this, I will connect this geometry to this conformal manifold. At this moment is just an aside comment.
Okay, thank you.
Okay, so let us discuss our final tool, and our final tool is the strongest tool that we will use. So in addition to counting 't Hooft anomalies, computing 't Hooft anomalies, and playing with these R-symmetry games and computing quotients about conformal manifolds, there are other various types of counting exercises that we can perform. And these turn out to be various types of Witten indices that we can compute. Okay, Witten indices, or alternatively certain localization computations. Okay, and computations. Okay, I will not discuss the localization part or facet of this of these tools in these lectures, basically because we will only discuss one particular type of Witten index that we will compute, which turns out to be an extremely simple gadget in 4 dimensions. It is a little bit more complicated gadget in other dimensions, but in 4 dimensions, it is an extremely simple one. So before we will define this gadget, let me remind you very, very briefly what the basic idea of Witten index is. Okay, so the basic idea of Witten index is, say you have a certain algebra, which a supersymmetric algebra, you have 2 supersymmetric generators, say Q and Q dagger, which are nilpotent, and that you have a supersymmetric algebra of the following sort, that Q and Q dagger is equal to some operator delta, okay, where delta is some bosonic operator. Usually it is, when you learn about the Witten index, it is the Hamiltonian, but it will not be, it doesn't have to be a Hamiltonian, it is some bosonic generator, and we actually, in a moment, will define it with as something else than energy. Then what you can compute is a certain quantity, which is called the Witten index. And this Witten index is defined in the following way. Okay, it can depend on parameters, which I collectively defined by you here. And then you compute the following trace over the Hilbert space of your theory with -1 to the f, where -1 to the f is usually called the fermion number. And under this -1 to the f, the supercharges are charged. Okay, they have f equals to 1, and the bosonic charges, say delta, has f equal to 0. So you trace over all the states in your theory with -1 to the f. Then you turn on e to minus beta delta, where beta is some parameter, some chemical potential, and delta is this charge appearing in the anti-commutation relation. And finally, you can introduce this U's, and there are some number of them, and this U's coupled to charges Qi, which commute with the choice of your supercharge, with the supercharge which is here. So it might be that your particular setup doesn't have any charges which commute with the supercharge, so you will not have these parameters U. And depending on the setup, you can have various such parameters. Now, important statement about these types of Witten indices is that they are independent of continuous deformations of the theory. The basic logic about this Witten indices is that states which have this delta, which is not equal to 0, always have to come in pairs with opposite fermion number. And then when you compute such a trace, these pairs always cancel each other. So in fact, although you define this index using this factor e to the minus beta delta, this index is not dependent on this parameter beta, because the only states which contribute to this index have beta, which is equal to 0. When beta is not equal to 0, the states do not have to come in pairs, and they do not have to cancel. And this constitutes a certain refinement of this counting. Okay, so this is a very standard statement about the Witten index, and in the notes I added a little bit of more systematic details. Again, because this index is this thing that, you know, when delta is not equal to 0, the states cancel in pairs, and they don't have to cancel when delta equal to 0. When you have a theory which depends on a parameter, states, the delta quantum number of states can change, but it only can change in such a way that if, say, the states, certain states had delta equal to 0, they can acquire delta not equal to 0 in pairs with opposite fermion number. Okay, so this type of an index is an invariant of such effects, and it is thus an independent quantity which is independent of such continuous deformation. In our case, we are interested in deformations which are like RG flow or decoupling on the conformal manifold. So for us, these deformations will be what we will want to be, or such quantities, we will want them to be independent of RG flow and exactly marginal deformations. Marginal couplings. Okay, so how to construct such a Witten index concretely given a conformal field theory? So first definition we will have, we'll use the superconformal algebra. Okay, so the index which we will define is usually called the superconformal index. Okay, and the particular type of algebra of this sort that we will use is some subalgebra of the superconformal group. As I have remind you in the last lecture, in the superconformal algebra, we have various generators. There are the generators Q, the supersymmetric generators, and there are conformal counterparts, which are usually denoted by S, and they satisfy an interesting algebra. Okay, this is equal to delta alpha beta, delta plus 3/2 R plus 2J 1 alpha beta. Okay, where delta is the scaling dimension, is the dilatation operator. R is the main hero of our lectures. It is the R symmetry in the superconformal algebra. And these guys J1, and there is another guy which is J2, are the generators of the SU2 times SU2 Lorentz symmetry of our space. Okay. So now what we can do, we can think of this gadget as beta as the Hermitian conjugate of Q alpha. Or basically, let me be more precise. We think of Q alpha dagger as a generator S alpha. And the way to think about it is that we think about this algebra or this kind of a construction as being done in the radial quantization. So in the radial quantization, you know, we're building our space from spheres, you know, along the radial direction, and then under inversions, these generators Q and S are conjugate to each other. And for example, the momentum P and the special conformal transformation K are conjugate to each other, and so on. So we basically define the conjugate of Q, or Hermitian conjugate, to be this operator S, and then we define this collection of bosonic charges to be our delta. Or to be more precise, let us choose a very particular supercharge. In this algebra, there are many supercharges. Let us choose a supercharge, which we'll call Q minus a half, which has quantum numbers of minus a half and a 0 under the two J's, the J1 and J2, which I did not write, the two Lorentz generators. And the R symmetry of this generator we will choose to be equal to +1. There are other supercharges. We can choose any one of them. So we just make a choice. And then we write this particular algebra for this element, this particular element of the algebra for this choice of the supercharge. So for this choice of the supercharge, we can write that this as being delta minus 2J1 minus 3/2 R, and this particular combination will define to be our delta. Okay, where J1 here is the Cartan generator of this SU2 rotation. And now this algebra is exactly of the same form as written here, so we can define the Witten index for this algebra. And this Witten index is called the Supraconformal Index. Okay, so it will depend on parameters which are usually called Q and P and U. And so let me define it precisely. So it is just trace of -1 to the F, e to the minus beta delta, as is true for any Witten index. And then in this particular case, we have a collection of combinations of bosonic charges which compute with our choice of supercharge. So we choose this fugacity Q to couple to charges which are J1 minus J2 plus half the R symmetry. And we'll define another fugacity P, which couples to J1 plus J2 plus half of the R symmetry. This combination of charges commute without our choice of a supercharge. So our index will depend on these two parameters, Q and P. So any n=1 supersymmetric theory, when we compute the index of it, can depend on two parameters, and these two parameters are usually called Q and P. And then, as in the case of a general definition of the Witten index, we can have a collection of other parameters, so other fugacities. So the other symmetries that we can have are global symmetries of the theory, in this case. So we turn on fugacities for the maximal torus of this global symmetry group, and these QIs are the charges of this global symmetry. And we can compute this type of index for any n=1 superconformal quantum theory. Any questions about the definition of the index?
I have a question for superconformal index. If we choose the different supercharge, can we get the same index?
Yes. So we have 4 different supercharges. So we can have, in principle, define 4 different quantities.
Yes.
But they're all related in certain trivial ways. So one of them is less obvious, but in all examples, they give equivalent indices up to redefinition of fugacities or conjugating various symmetries.
Okay.
I will
Thank
have
you.
In a couple of minutes, we'll write explicit expressions for the index, and I will make a comment, showing exactly where these choices will come about.
Okay, thank you.
So, yes.
Yeah, can you elaborate more on what are these U, Q, and P's? You said there are some parameters, but
This use?
more. Yeah, U's, Q's, and
P's. So these by themselves are just numbers. Okay, I just some parameters that are not related to your theories. These are just some numbers that we pick. Okay, so just some formal numbers. What is important is that when we trace over the states in our theory, we weigh the states with these weights. And the weights of each state are, we compute what are the quantum numbers under these various symmetries that we have, the J1, J2, and the R symmetry. And the way with this state with Q to this power, P to this power. And then if the state is charged under some global symmetry, we weigh it also with some product of these U's. Okay, so
okay.
these are just you can think of it just as some thermodynamic partition function. These are just fugacities which couple to certain symmetries. The only important thing here, which makes it so powerful, is this -1 to the F. This is why this is invariant under various deformations, and we can exactly compute it.
Okay, thank you.
Okay. So now that we have to define the superconformal index, we use the superconformal algebra. but we want to define an index which is invariant of our G flow. Okay, we wanted to, the questions that we want to answer is starting from some UV theory, we want to understand the infrared physics. During this flow, when we start from the UV CFT and we turn on a relevant deformation, we break conformal symmetry. So we cannot use the superconformal symmetry to define any index. And here there is an important twist on the story. Historically, it was actually, the whole story was done in a completely opposite order. But as was shown by first Rommelsberger, who was the first one who defined the index a long time ago, and then by Festucci and Seiberg, who did it rigorously, there is a way to define this index without making use of superconformal symmetry, exactly the same index. And let me just mention how it is done. So we think of the index not as this trace over the states of our theory, but we think of it as a partition function on S3 times S1 with supersymmetric boundary conditions around this S1. Then you analyze, this is a curved background, so you analyze what are the supersymmetry which are preserved on this background. And there is a way to preserve certain supercharge Q and a certain R symmetry R. And you also have the rotations or translations around this, this circle S1. And if you do that, you actually generate an algebra which is very similar to the algebra which is given here. Not just similar, but actually precisely the same algebra. And again, the point is you lose the superconformal algebra, but again, you keep this very important player, the R symmetry. It's very important that the flows that you are considering are preserving certain R symmetry. If you do that, you can define this partition function on S3 times S1 to preserve certain supersymmetry algebra, which is exactly of this kind. And then you can define the Witten index as you always define it. During the flow, this is not related to superconformal symmetry. It is just some other index that you are computing. But at the endpoints of this flow, the index that you define in this way as a partition function coincides with the superconformal index. So if you wish, you compute this index at the UV fixed point with the charges that you preserve under the deformation. And this, the result of this computation is the index of the infrared fixed point. So this is an extremely strong tool to give you an RG invariant of a certain RG invariant, which is very, very rich. And now we will discuss what kind of information you can actually extract from this index about the fixed point. Okay. So let me discuss another way to think about the index. So the index is this certain function of various parameters, this U's and the Q and P, and it is a trace over the states of your theory. So since you have states in your theory and at the fixed point, you have the superconformal symmetry, and again, we now think about the superconformal fixed point, we can expand in terms of characters of the representations of the various symmetries that we have. So we can expand it in terms of these multiplicities of various representations. Then we have these guys I call chi of R and L, which are function of Q and P, which are indices of certain irreps RL of the superconformal group. And then we have the global symmetry group, and I will label the representations of the global symmetry group by M, and the characters of this global symmetry will be this chi of M of U. So we can think of our index as this type of an expansion, as determining these numbers N, L of M of various multiplicities of various representations that we can have. Now, the important thing is that this decomposition is not well defined. Okay. And why is it not well defined? It's not well defined because the index is defined with this -1 to the F. So various representations, for example, can cancel out. It might be that, you know, you can think of your index as having a certain multiplet and plus another multiplet which contributes with exactly the same contribution but with a minus sign, or not having any of these combinations at all. Okay, the fact that you have this -1 to the f makes this expansion in terms of these multiplicities ambiguous. Okay. However, there is yet another way to think about this expansion, and instead of expanding in characters of representations of this superconformal algebra, you expand in terms of certain equivalence classes of representations. So we will define equivalence classes of representations with the square brackets, and two representations are equivalent or belong to the same equivalence class is if they contribute plus or -1 the same to the index. The same to the index. Okay. So a representation which contributes certain contribution, and a representation, any other representation which contributes in the same way or minus the same way, we'll consider to belong to the same equivalence class. And then we can expand the index in multiplicities of such equivalence classes. So again, sum over L over M, and then we have these other multiplicities, which are called net degeneracies. And then we have these characters of a representative in certain representative in this equivalence class, and again, characters of global symmetry. Okay, this analysis was done by Beam and Gadet, and this will be a very important ingredient in our discussion. Now, these numbers are well defined. Okay, you can extract them. These net degeneracies you can extract from the index. And now the very important thing that Bimve and Gadet did is they looked at low orders in the expansion of the index in these fugacities Q and P. And they have realized that actually, if you look at these low orders, these net degeneracy, sorry, these equivalence classes of representations have very interesting form. So if you look on an index of a superconformal field theory and you compute it with a superconformal R symmetry, again, it's very important that you identify the superconformal R symmetry correctly, and you assume that there are no free fields at the fixed point, that your CFT doesn't decompose into some free fields and interacting part. Then there are these two following very important statements that you can say. So first of all, if you look at the expansion of the index at terms which are weighed with certain power of Q and P to the n, such that n is less than 1, n is it might be a fraction of power which is less than 1, then the only operators which contribute to the index are relevant operators. Only relevant chiral operators contribute to the index. Okay, so the only element in the universality class which would contribute at this order are relevant chiral operators. So you can cleanly extract relevant operators from the index. Moreover, if you look at the order QP in the expansion of the index, there are two elements in the universality class which contributes at this order of the index, and these are marginal operators. So you will see the character of the marginal operators, which might depend on you, minus the character of the conserved currents. Okay, which of course are always in the joint representation of your symmetry group. So marginal operators and the conserved currents contribute at the same order in the index, but with an opposite sign. Okay, so these are the two things that you can most cleanly read from the index. You can read of the relevant operators and the marginal operators minus the conserved currents. Of course, the fact that the marginals and conserved currents, you know, they interact with each other should not be a surprise to you at this stage, because we went to a great detail to discuss that marginal operators can recombine with conserved currents to form marginally irrelevant operators. Okay, so it should be that in the index they will appear in a similar way. Okay, and why is it important? Again, it will be a very useful tool, and I hope I will do it already today, to understand, for example, emergence of symmetry in the infrared. Since in the index you can read off the representation of the global symmetry group, we will be able in certain cases to understand or to show that a certain theory has an emergent symmetry. Are there any questions about this? Okay. So finally, before turning on to dynamics, let me mention that the index is extremely simple to compute. And let me just give you the basic rules of the computation of the index basically in 2 or 3 formulas. So the way to compute the index is that if you have a chiral operator, let's call it Q, and the R charge of this operator is some number R, and it is in a representation, this curly R of your global symmetry group, such that the character of that representation is like that, then you can easily compute the contribution to the index of this chiral field with this simple formula. Okay, so this is some function of Q and P and the fugacities for the Cartan generators of your symmetry group, and you get this type of an expression where you can think of the various terms which come into the index as coming from various components of this chiral multiplet. So, for example, this term in the numerator of this exponent comes from a scalar in this scalar component of this chiral superfield, and this comes from the conjugate fermion. And to the question that I was asked before, that if you choose another supercharge, for example, then what will contribute to the index will be a conjugate of the scalar and the fermion, and not the conjugate fermion. And then correspondingly, the representations will be conjugated. So upon this simple, except for this simple variance of the index, the indices will be equivalent. Okay. And now the important thing is that this type of a function, this function looks very complicated, but actually it is a standard by now special function, which is called an elliptic gamma function. So if you define an elliptic gamma function using this type of a formula, then the contribution of the chiral multiplets Q to the computation of the superconformal index will be some kind of a product of these elliptic gamma functions. And finally, if you want to compute an index of a gauge theory, then you need to know the only thing you need to know is the index of a theory before you gauge a certain symmetry. And let us define that index to be function I1 of Q, P, and then 2 sets of fugacities, U and V, where the fugacities V correspond to the symmetry you want to gauge, and U correspond to the global symmetry. And then the index of the theory with that symmetry gauged is just given by some kind of an integral, okay, of this type, of this sort. Okay, so this is the index of a theory where you gauge the symmetry V, and it has you just take the contribution of the theory with the global symmetry. This is the thing I marked in green, and then you have a contribution of vector multiplets, which you introduce when you gauge, which I marked here in orange. And this guy here is the Haar measure of the group that you gauge, and then you just integrate over the maximal torus of your gauge group. Okay, so this is a very, very well defined procedure that you can rather easily perform. Okay, And the end result will be the superconformal index. And this superconformal index will encode a lot of information about the fixed point in the infrared. Okay, and I will write more expressions as we go on, and I hope this procedure will become clearer. Okay, with this, I end this first part of discussing the basic tools, and I want to start discussing the interesting dynamics using these types of tools. Any questions? Okay. So let me start discussing dynamics. Okay. So the way we will proceed, I will give you a very brief review of very well-known results, basically the Seiberg duality for special unitary groups. And then we'll discuss much less known results, interesting results of emergence of global symmetry and conformal dualities. And eventually we will have a geometric explanations of these strong coupling effects. So the first thing I will do, I will discuss a certain collection of simple theories of the sort that we have already encountered. So let us consider a theory that I will call A, which is just SUN SQCD with NF flavors. Okay. Remember, this is exactly of the sort of the theory that we have discussed in the beginning of this lecture and in the end of the last lecture, but the NF was equal to 3n. Now I will take NF to be unrelated to n. It is just an additional parameter of this theory. So we have NF fundamental fields, and we have which we'll call Q, and NF anti-fundamental fields, which we'll call Q tilde. Okay, and here comes the statement of Seiberg duality. So these theories satisfy very interesting property. So if you choose this parameter NF to be in the window between 3n and 3/2 n, then the following statement holds. There is another description that you can define, which is in terms of SUNF minus n SQCD with the same number of NF flavors, which will now denote, instead of capital Q, by small q's, q's and q tildes. Again, these are in fundamental and anti-fundamental representation. And we also add gauge singlet fields that we will denote by M, and we turn on a superpotential which couples this M to Q and Q tilde. So the number of these fields M is an F squared. We have an FQs and FQ tildes. So we have now an F squared of these M's, and we couple these fields with this type of a superpotential. And the statement is that these two theories, the theory A and theory B, flow to exactly the same fixed point in the infrared. Okay, so we can start with a CFT A in the UV. We turn on the gauge coupling, and then we flow to CFT in the infrared. Or we can start from this other CFT, which we call CFT-B, which has a different gauge group. Okay. Instead of SUN, we start with SUNF minus n gauge group, and we flow to exactly the same fixed point. Okay. Here, the deformation is not just gauging. Okay, it's also a superpotential deformation. Okay. Now, there is another statement. If we go outside of this window of parameters, which is usually called the conformal window, as this theory in the infrared is believed to be strongly coupled as CFT, another statement can be made. So if you consider the number of flavors to be smaller or equal to 3/2 n, but bigger or equal than n plus 1. This is a a second type of a setup. You can consider the same SQCD theory A that we have defined above, and the same theory B that we have defined above. So there is no need to define anything else. The only thing is that this theory A will still have, as in the case we have defined above, trace R G squared to be positive, and thus the gauging will be asymptotically free. However, here you will get the trace R G squared will be negative. So the the gauging in this theory will be IR free. So this theory will flow to a free theory in the infrared. And the statement here is not the statement of the duality that we have discussed, but rather that you start with theory A and deform it by this gauging that we have discussed. And then we have flow to a certain theory in the infrared. And the statement is that the effective theory in the infrared that you get is this IR-free theory, which we defined as description B. Okay, so you undergo here some region of strong dynamics, and the theory that you get in the infrared is very different theory than the one you started with. Okay, so if you, another way to phrase this statement is that as this theory is IR-free, you should ask yourself how can you flow back into the UV and define this theory consistently? Well, you can do that, and then the UV completion or consistent or good description of this theory, IR-free theory in the UV, is the description A. Okay, so these are the basic statements of Seiberg duality. Okay, there are various checks that of this duality that you can perform. So let me here just mention a very simple, the check, one of the RG invariants that we have mentioned, the supersymmetric or superconformal index, how it will work out. For example, if you want to compute this supersymmetric index in the case of SU2 gauge group with an F equals 3, sorry. Okay, so just take the theory A to be SU2 SQCD with an F equals 3. Then by this statement of Seiberg duality, it will flow to a simple theory in the infrared. The theory in the infrared will be SU3 minus 2, which is SU1. You don't have any gauging, but you will have a certain collection of fields. You will have these fields M that we have introduced, and these quarks, Qs, and Q tildes, which will couple through certain superpotential. And so you will flow to just a West-Zumino model, and then you compute the index of this theory using the tools that we have defined, and you will obtain that computing the index using the description in description A, it is some gauge theory with SU2 gauge group. You will get certain integral, and this is this integral which is written here. But using the description B, you don't have any gauging. You just have a collection of some chiral superfields. So you will have just a product of these elliptic gamma functions. And if the duality is correct, this equality needs to hold. You might got an impression that this, the correct impression that these elliptic gamma functions are complicated functions. So this is a rather complicated identity which needs to be satisfied if the duality is correct. And I encourage you to just plug this type of identities into Mathematica and see that they actually work. The proof of these identities is rather non-trivial. And amazingly enough, this was done in the last 20 years or so. Although, these are beautiful mathematical identities. And they need to be satisfied if Seiberg duality is correct. Okay. Any questions about this? Because we will use these types of dualities as building blocks into understanding more complicated physical phenomena. Okay. So I have How many more minutes can I go, Wenbin?
I mean, I think it's a good, I'm not sure, depends on you, but I think this is a good time to just maybe stop and taking questions. Since we have 15 more minutes. It also depends on your schedule.
Yes, I'm behind the schedule, but that's okay. I will speed up a little bit next time. But please ask me questions now if you have any questions about what I was discussing. And if not, I will go a little bit further. So are there any questions about everything we discussed till now?
I have a question.
Sure.
When NF equals to 3/2 n, then the theory B is just a safety IR.
Yes.
Uh-huh.
So in that case, you know, the dual theory is exactly the theory with the marginal coupling that we have discussed, which we know is AR free. So the theory with the 3/2 is asymptotically free, but it flows to this free theory, which you can describe with the coupling, which is marginal, but it is marginally irrelevant.
Okay, thank you.
Okay. If there are no more questions, I will use another 10 minutes and set up a physical theory which will turn out to be very interesting and which we will discuss next time. So, okay, these are the Seiberg dualities. This is something which is very well known from mid-90s, and there has been a lot of developments. So now let us look at one of the simplest theories that of this type, SQCD with a simple gauge group, and use our technology that we have developed to say something very interesting about it, which in the end will be related to Seiberg duality, but it will not be obvious the way we will set up this discussion. So I want to consider an SU2 gauge theory with 4 flavors. Okay. So again, what this means, an F equals 4, it means that we have 4 fundamental fields and 4 anti-fundamental fields. But as the gauge group SU2, there is no real difference between fundamentals and anti-fundamentals. So this theory is basically SU2 with an octet of fundamental fields. And here I will introduce a notation, which is called the Quiver notation, which is very useful to visualize the various theories we are going to discuss. And the notation is as following. I will, every time I have a gauge group, I will write a circle, and we will only have SUN types of gauge groups. So inside the circle, I will write the type of the gauge group we have. So this circle will mean SU2 gauge group. And then the arrows will correspond to bifundamental representations of certain symmetries. And the things which transform in these bifundamental representations are the chiral fields. So this theory actually has an octet of fundamental fields. And let's denote them by Q. So the Quiver theory that we will write is a circle with a 2 inside it, an arrow between the 2 and an 8, where this stands for SU8 global symmetry group of the theory. Okay? This is just a depiction of this theory. So this is a very simple theory. And what we will do, we will deform it a little bit, and we'll arrive at a very interesting effect of emergence of global symmetry. So first of all, we need to understand what is the superconformal R symmetry of this theory. And the statement is that the superconformal R symmetry of these fields Q is a half. Okay, so a way to understand that is, again, to do a maximization and so on. But here it's actually very simple, because the only non-anomalous symmetry that this theory has is SU8. So the only thing you need to find is a non-anomalous R symmetry, and the only non-anomalous symmetry that you can assign to these fields Q is R of Q being a half. Okay. So this is what I want you to know about this simple theory. And now let us use it as a starting point and deform it. Okay. So what we will do, we will take this SU2 SQCD with 8 fundamental fields, and we will split this octet of fields into a 6 and into a 2. Okay. Just when I do that, I did nothing. So what to actually do a physical deformation, I will give a meaning to this splitting. I will introduce another set of fields, which are gate singlets, which I will call M. And these fields M will couple through a superpotential to a certain gauge invariant combinations of the fields that are written here. So let me call these fields Q, these 6 fields Q. And these fields, which are the fields, these 2 fields, 2 fundamental fields, I will call Q tilde. And I will introduce a collection of fields, 15 fields M, and they will couple to in the following way to the fields Q. So I will have MAB times epsilon ij times QIA QJB. Okay. So there is an epsilon symbol here, which will make sure that this combination is gauge invariant. But since I anti-symmetrize these indices, I need to anti-symmetrize also these indices. These indices run from 1 to 6. So this anti-symmetrization will give me 15 different operators. And all of these operators, I couple to these new fields MAB that I have added here. Okay. So what we need to analyze first is whether this deformation is a relevant deformation. Okay, so for that, we need to compute the R symmetry of this superpotential. What is the R symmetry of this superpotential at our starting point? So the R charges of the fields Q that I mentioned are equal to half each. Okay, and the R symmetry of these fields M is equal to 2/3. These are the free fields that we added at the fixed point. Okay, so clearly this number is smaller than 2. Okay, so this deformation is relevant. So this theory flows to a new fixed point. Okay, so we will introduce actually another useful notation. These fields M, I will denote as this cross on the quiver. Okay, so what we will show next time is that this very, very simple theory has a very interesting property. So the global symmetry that you see here in the UV is SU2 times SU6 that you explicitly see by splitting this 8 into 6 and the 2. And actually you have another U1 symmetry, okay, in this splitting, which is non-anomalous and preserved by the interaction. And what we will show is that this theory actually has this SU2 times SU6 symmetry enhancing to a 6. Okay, and the way we will show it is by computing the supersymmetric index and extracting from it the conserved currents in the infrared. Okay, and we will see that conserved currents of E6 appear. Okay, so this will be a rather simple but surprising instance of emergence of symmetry, which we will again have a geometric explanation of later on. Okay, so I think here it will be a good point to stop for me. Okay, any questions?
There is no other statement about Seiberg duality for other than the 2 windows that you mentioned.
What do you mean?
I mean, when NF satisfied, when NF was greater than or equal to 3/2 and less than 3n, and the other case when it was between n and.
You mean for smaller NFs?
Yeah, capital NF.
Yes, when an F is too small, the dynamics is very different. So there is this simple dynamics that we have discussed, is dualities and so on, when an F is bigger than N. Okay. When an F is equal or smaller than N, the dynamics is very different. There are certain non-perturbative effects that can come into the game, and there are no such dualities. Okay, kind of a hint that you can get that things have to be very different. In these cyber dualities in description B, the gauge group is SUNF minus N. Okay, so if an F is equal or smaller than N, it's clear that this will be nonsense. So something else needs to happen. So I will not review what happens in those cases here, but this dynamics was analyzed by Seiberg and others, and it is very interesting, but it is quite different.
Okay, thank you.
By the way, Shlomo,
Yes.
would you mind if we upload your recording of your talk later to the into YouTube?
Sure.
Okay, great. Thanks.
So I'm rather behind on schedule. So let me know if you like, or now, or I don't know in which way, whether I'm going, it's too simple or too hard, because I have hard time to judge it. So I can speed significantly up if it is not hard enough.
Yeah, and okay, I guess everyone, if you feel simple or hard, it's okay. You could type your opinion into the chat window, so we have a better judgment.
So again, in the notes, I have put more details of everything I have said, and there are exercises. And I really, if you want to understand this subject, as any subject, I really recommend to do the exercises. Most of them are very simple. Some of them are more complicated.